Hello. Okay, so we are on Tuesday, and so let me just kind of outline the way this is going to look. So today, I'm going to show you polyprotic acids. That's today. Tomorrow, I'm going to do acid-base properties of salts. And then the last thing is going to be, sorry, that's not tomorrow. That's Wednesday. And then Thursday will be the last day, and that will be explanations of acid strength. So I'll get into kind of like why certain acids are the way they are, and it seems like every time I do this, my washer's on. I don't know. But, so at some point that'll beep. But today we're going to talk about polyprotic acids. This really shouldn't take too long. I'm only going to give you a couple questions. I also did, set up a review sheet, and I'm going to describe how I'm going to do it, but I'll send that to you today. You could do most of it. There's a few things you can't do yet. But let's go through this. And I'm just going to describe a couple things. So polyprotic acids have more than one acidic H plus or proton. Sometimes you'll see, sometimes it'll be an acidic proton. And so what's going to happen is if I take, the classic polyprotic acid is H2SO4, and H2SO4 is a really, really strong acid. So it actually is going to have two Kas. So they call it Ka1 and Ka2. So the Ka1 is going to be the first dissociation, and then Ka2 is the second. This Ka1 is always larger than Ka2. So the first proton that comes off it's always going to be easier to remove the first one than it is going to be to remove the second one or the third one. So H2SO4, what's going to happen is you are going to end up with reacting it with water, and I'm drawing this single arrow so you can see this is going to be almost 100% this way, forming H3O plus AQ. Once again, the H plus is going from there to there, and you're going to form HSO4 minus AQ. And now I'm going to mention a term that I'm going to talk about. I should have mentioned it before, but you see how this HSO4, it still has an H on it? This H can be removed. And so if I said, I've got a 1 molar concentration of H2SO4, and I told you, oh, this is a strong acid, and I kind of had you highlight H2SO4 as pretty important molecule. H2SO4, the first protonation is very, very strong. So that means that if I have 1 here, I'm basically like at the end, it's going to have 0 at the end. Like if I did a minus X plus X plus X, I'd end up with 0 here because H2SO4 is such a strong acid that I'm going to end up with nothing here. And these ones are just going to be both 1s. Okay, so H2SO4 is such a strong acid that I'm going to end up with a 1 molar here and a 1 molar there. So in most cases, that's just the normal way strong acids do stuff. But what's going to happen here is the HSO4 is still going to have a proton that can come off. So let me mention one thing. If you look up in the charts, you'll probably see the Ka1 of H2SO4 will just be called large. It's such a large number. The Ka2 is 1.2 times 10 to the negative 2. So that means that if I just had this in solution and I put it in water, it's gonna behave like an acid with a Ka2 of 1.2 times 10 to the negative 2. So what's gonna happen is this one will be an equilibrium, because that's like the weak acid move, is to make it an equilibrium. Then you'll form H3O plus and SO4 2 minus. Now in this case, I've got a problem here, because right away I'm just going to use my equilibrium. I'm going to use my equilibrium from over here. So now HSO4 is going to start with that. I'm not going to have any SO4, but I am going to start off with an H3O concentration of 1.0. Okay, so that's like the big difference with polyprotic acids, is the second protonation, you're going to end up with a 1.0. And then it's going to follow the same rules, x, 1.0 plus x, 1.0 minus x. And this one, we're actually going to need to use our Ka2. So it's going to look like Ka2 is equal to H3O plus times SO4 2 minus all over HSO4 minus. And we plug in these numbers. 1.2 times 10 to the negative 2 equals 1 plus x times x over 1 minus x. Hopefully I'm getting that there. There you go. 1 minus x, and you solve for x, and whatever you get, I don't have my TI-89 right on me right now, but whatever you get, I'm going to add it to the H3O, and whatever that final is, I would take the concentration of this H3O plus and then add it, like add the x to the 1.0, and then I would go negative log of this one will give me my pH. Okay, so whatever x is, I would just pop it there. Okay, so I also want to just highlight a couple things. This HSO4 reminds me that there's a thing called a amphiprotic species. So I'm going to give you another one of those in a second. Okay. Amphiprotic species are usually it's a Bronsted-Lowry substance that can act as an acid or base. The easiest way I can make this for you is I've got a list. NH3, H2O, and any negative ion with an acidic H+. And that means it can accept, or I'm sorry, donate or accept an H+. Like that's usually what you would go by, is the acids or donators, bases can accept, but some things can do both. So if you see amphiprotic species, NH3 is a classic one, H2O is a classic one. Now, NH3 is normally thought of as a base, H2O is commonly thought of as neutral, but depending on what it's reacting with, it can act as an acid or base, and then any negative ion with an acidic H+. So if I said HSO4 minus, and I said, what is that possible to be amphiprotic? You would say yes, because it's a negative ion, and it has an H that can be, it's got an acidic proton. By the way, sometimes you'll hear people saying, not regularly, but sometimes you'll see that word as well. Amphoteric and amphiprotic kind of mean the same thing. I usually like to think of it as an amphibian, like a frog can swim or live outside of water. or live inside water, amphiprotic species are things that can, do both with protons. So that's a good way of thinking about it. And this is a nice little algorithm that you can pretty much always use. So classic question you'll get is, tell me the thing that's amphiprotic, and it's usually one of these or these two. Okay, that's just an extra side. And so let me do one more polyprotic example here. So oh boy, that's a big one. All right. Arsenic acid. This is going to be kind of annoying. I might have to write small. Ka1 is 5.5 times 10 to the negative third. Ka2 is 1.7 times 10 to the negative third. Seventh. And then Ka3 is 5.1 times 10 to the negative 12. And then they ask for a lot of different stuff. Okay, so I may need to run upstairs and grab my TI-89 for this one, but let me show you kind of to start this off. Arsenic acid is H3ASO4. Okay, so this is a triprotic acid. So the first reaction is going to do is H3PO4. Can you guys see that okay? I think so. AQ plus water forms H3O plus H2. I want to write phosphate, and it's not. H3ASO4 and H2ASO4 plus. Both of these are AQ, and it says it's got a 0.2 molar triprotic acid. So it's 0.2 here, 0, 0, minus x plus x plus x, 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 and 0.20 minus x. I don't think this is small enough to do that thing, so I have to go x squared over 0.20 minus x equals 5.5 times 10 to the negative third. And I'm going to have to get my TI-89. So I'm going to stop this, and then I'll start it again.